Hello and welcome to this exciting video tutorial on vector rotation by matrix multiplication. Have you ever wondered how algebra, specifically matrix algebra, plays a crucial role in real-world applications? Today we are going to uncover the fascinating world of inertial navigation systems and demonstrate how multiplying vectors with matrices results in rotation and scaling of the vector. By the end of this tutorial, you will not only grasp these mathematical concepts, but also understand their practical applications in cutting-edge technologies such as INS. Let's dive in. So this is how an inertial navigation system looks. INS are sophisticated navigation devices used to calculate the position, orientation and velocity of a moving object such as aircraft, submarine, etc. without the need for any external reference such as GPS, GLONASS or any other radio aid. These systems are widely used in a variety of applications including aviation, spacecrafts and missile systems. They are highly reliable and accurate in environments where external navigation aids are unreliable or unavailable. First, let's understand the local tangential frame, commonly known as north-east down or NED frame. This coordinate system is pivotal in navigation. It consists of three axes, north, east and down. So at this point of time, our vehicle or aircraft is at this location, and through this location there's a longitude which is passing, and also this location has a latitude. The idea first is to establish the correct coordinate system in which we are going to navigate. So a tangent to this longitude points to the pole or north pole, which is what this axis is all about. Then another axis which is perpendicular to north is the axis which is passing through the center of Earth. It is called down. And another one which is perpendicular to both these axes is the east axis. So once we know where north and east are, our problem to solve navigation equations become much easier. Note that the center line is the equator and this is the prime meridian. So essentially we have to navigate using this coordinate system, and this is what is called as local navigation frame. And how it is done is that essentially INS consists of a sensor assembly. This blue plate is the sensor assembly. It is consisting of three gyroscopes which are keeping track of angular motions, and there are three accelerometers which are keeping track of the linear motion of the vehicle. And through these gimbals, there are three of them, green, blue and this gray one, we are trying to rotate these gimbals in a manner so as to achieve alignment with this north, east and down. Once we have achieved this alignment, then it becomes very easy for us to know our position, velocity, acceleration, etc. through the method of dead reckoning. So here is a practical inertial navigation system. Let's watch a fascinating video featuring two gimbaled inertial navigation systems, one from an American aircraft and this is from the Russian aircraft, MiG-21. You can see the gimbals in action. You are not able to see the sensor assembly inside it. And notice how once we power up this system, all the gimbals, they get aligned, and now we are going to move around this simulating the aircraft movement, and you can see that the device is tracking the aircraft motion. See how the gimbals are aligned. In practical application, these gimbals will be aligned with north, east and down frame that we talked about. Having understood the local tangential frame, now let's try to understand the modern inertial navigation system where these gimbals have been removed, and the functionality of these gimbals is mimicked by mathematics. And this is a very important concept. So first we understand the body frame. In body frame, the sensor assembly is directly mounted to the body of the aircraft, which has a roll axis, pitch axis and yaw axis, and there are no gimbals in the system, and that's why it's called Strapdown INS. And the problem now is that when this aircraft, so you can see the coordinate system here, this is the body frame. This body frame is attached with is fixed with the body of the aircraft. So when this aircraft does maneuvers, this frame rotates along with it and goes in misalignment with the NED frame. And hence, since the gimbals are not there in this system, in the strap-down system, we have to do something to make sure that the body frame of the aircraft realigns with the north, east and down frame, which is the navigation frame on the Earth. So this is what is done through matrix multiplication, and that's what we are going to discuss. So as I mentioned, this is the body frame, this is the roll axis of the ship. This is the pitch axis of the ship, and this is the yaw axis of the ship. And as the ship is moving, this coordinate system is moving along with it. So rotation is being tracked through gyroscopes, and the linear motion is being tracked through accelerometers. And here you can see the entire strap-down INS. You can see that there are no gimbals inside it, and there are three of them perpendicular to each other. Basically, in a strap-down INS like RLG, it uses Sagnac principles, where two laser beams are sent in opposite direction, and one beam, because of rotation of the platform, will experience shorter path than the other beam, and this will create path difference leading to interference patterns, and that's what are read. So why these gimbals have been removed is basically since there are no moving parts, the maintenance becomes very easy. The reliability, accuracy, etc. is very high in comparison to gimbal systems. This is another ring laser gyro in action. You can see this ring laser cavities. They are not mounted on any gimbals, and there are 3 of them: one for the roll axis, one for pitch, and one for the yaw axis. So we are not going to deep dive into how the entire INS works. Idea here is to show that how mathematics is mimicking the functionality of mechanical gimbals through matrix algebra. So in this slide, you can what I'm doing is that I've taken a vector which is 1 1 column vector, and I'm taking a random matrix M 2 by 2 matrix as shown on the screen, and I'm trying to multiply this vector V with this matrix, which results in a resultant vector or rotated vector called R. And let's plot this vector R and see what happens. So this is M, this is V, and the result is 1 minus 1. So effectively what happens is that when this is the vector V, so you can see that x-axis is 1 and y-axis is 1. This is what is being depicted here. And when we multiply this vector by any random matrix like this vector will rotate as well as scale. It can scale up or scale down, and it also rotates from its original position. So matrix multiplication is nothing but it is actually vector rotation. And in a very special case called eigenvectors, if you multiply eigenvectors with the matrix, it does not rotate. So that's not the core topic here. What we're trying to show here is a special form of matrices which causes perfect rotation of vectors, and they are called direction cosine matrices or direction cosine matrix. So essentially this is how it looks. We have some angle of rotation, and say coming from roll sensor or pitch or yaw, any of these, and we read that sensor and construct a matrix like this: cos of angle minus sine of angle, sine of angle, and cos of angle. This might be roll or pitch or whatever. And the property of this matrix is that it is a perfect rotation matrix. It does not stretch the vector either longer or shorter, and yet it is able to rotate the vector in perfect circle. So again, we are going to multiply it with our original vector v1, v2, and as you can see, the end result is this rotated vector. So let's have a look at this animation. So by continuously multiplying with this DCM, the original vector is rotating depending on the theta that we have specified. So here theta is going from 0 to 360 degree, and as you can see, this vector is rotating perfectly in a circle. And this is a two-dimensional 2 cross 2 DCM. The same thing can be achieved in 3-dimensional using 3 different DCMs. So if we have to rotate a vector in 3 dimension, as I mentioned earlier, we have to multiply that vector. Firstly, that vector has to have 3 coordinates, so v1, v2, v3. And then it has to be multiplied by 3 direction cosine matrices as shown in the slide. These 3 matrices can be roll, pitch, and yaw. And because of multiplication action, this vector is then going to rotate in 3 dimensions. The end result of multiplying these 3 matrices with this vector is a rotated vector, which can be described by these equations. So let's have a look at it. So this is the original vector in 3 dimension, and if I now multiply by these 3 DCMs, this vector can rotate freely in 3 dimensions. So once we know that a vector can be rotated in 2D or 3D using special kind of matrices called direction cosine matrices, then we can use this knowledge to rotate the body frame of the aircraft into the north, east, and down coordinate system using direction cosine matrices. So in this tutorial, we have covered the exciting world of vector rotation by matrix multiplication. We will implement all these concepts in Python in the next section.